well, actually, we're going to see these topics, but probably much sometime later. Anyway, we continue now with the variables we have introduced, quasi-local scalars, the Q scalars. We're now going to see some properties. And for example, something interesting is that we have analytic expressions for these scalars. See? First of all, notice that the metric we're using is the FLRW-like metric. See, in fact, you can use this metric even without the Q scalars, even with the traditional variables. It's just a parametrization, but we have seen how applying the formula, the definition that I gave yesterday, you can generate the Q scalars. For example, the Q density, the Q curvature, and the QH Hubble, they have very similar laws. They are like formally, they are identical to the FLRW objects. However, we know that they are not identical because the FLRW objects depend only on time, while this depends on time and radius. We see that the Friedman equation is almost identical. It's almost identical to that of the. Notice that the density and the Hubble scalar, not the Q scalars, the local. See, in order to distinguish between the Q scalars and the normal scalars, I'm going to call the other scalars, I'm going to call them local scalars, right? The normal density, the normal Hubble factor, those are going to be, I'm going to call them either local scalars or standard scalars, so that you understand what I prefer. Notice the equation that is satisfied, the Friedman equation that is satisfied by the Q scalars is this. Right? This is the equation, the Friedman equation satisfied by the Q scalars. Now, I don't know if you remember, but the Friedman equation that is satisfied by the local scalars, by the standard scalars, was this. This was the equation satisfied. It is back in your notes. See? This is a Friedman equation satisfied by the normal scalars, by the standard scalars. Not the same. It is different. The difference is this term here, the contribution from the shear. Right? So this is identical to FLRW. FLRW satisfies exactly the same Friedman equation, but HQ goes to H bar, and rho Q and KQ go to their Friedman quantity, right? See? This is identical to the FLRW form. And this is the nice thing about the Q scalars. We found by a nice procedure that it's a weighted average distribution. We constructed quantities that look very much like FLRW quantities. They have the same scaling laws. They have the same dependence on the scale factor, right? But they are LTV objects because they depend on radius. They are not FLRW quantities. They look like them, but they are not like them. See? So this is interesting to bear in mind in order to understand the properties of these objects. Now, we need to find First, the local density. Now we have the quasi-local density, but it would be nice to have an analytic expression for the local density. But the local density, it's going to be defined in terms of a fluctuation. So essentially what I'm writing here is I'm defining a fluctuation of the, say, I'm going to say, I already have the quasi-local density, and then there is also the local and the standard density. They are not the same unless we go to the homogeneity limit, then they become the same. But in general, they are not the same. So I'm going to define a fluctuation that is going to be simply rho minus rho cube, right? This is the simplest way to compare them. One minus the other. They are the same, fluctuation is zero. This is a standard procedure that we would do with quantities that have some connection with an average, right? Fluctuation of individual elements of the sample with respect to an average. Except that, remember, that here rho and rho cube are being compared at the same boundary, at the same two-sphere. That's what I explained to you yesterday, the difference between local and quasi-local fluctuations, right? I mean non-local and quasi-local fluctuations, okay? Notice that this formula is the same as this one. See, I'm writing something like this. Rho is going to be rho cube times 1 cross delta rho, okay? So this means that rho, this means that delta rho is nothing more than this. Is a relative fluctuation. Is a fluctuation relative to the average distribution. Remember that this is an average distribution, not an average functional, because of what I explained yesterday. So this is another way. The difference between this and this is that this is dimensional. It has the dimensions of the object, because it's simply a subtraction. On the other hand, the second one is dimensionless, because you divide the fluctuation, the units necessarily cancel. Now, for some purposes, it's better to use this one, and for some purposes, it's better to use this one. Like for analytic work, the dimensionless fluctuation is better. But for numerical work, the other one is better. Can people have figure out why? Why the one below is not so good for numerical work? Why? What can go wrong in the one below?
Because here as EQ goes to 0.
If the denominator goes to 0, you are in trouble.
Go to infinity.
Yeah? So, okay. Now, the density going to 0, we can say never happens. Because in cosmology, we know that the density far away will not go to 0, but to some background value. So, for the density is safe. But can people think, for example, if I write something like this, this thing can go bad, can blow up and behave very badly if HQ goes to 0, right? So when would HQ, in which circumstances would HQ go to 0?
When t goes to infinity, exponential expansion would be, scale factor will go to infinity. H is equal to A dot upon A.
No, but that's not.
Lambda
No.
is equal to 0 and kq is equal to eq.
Closer, getting closer. No. HQ can go to 0. Remember that this is A dot times A squared. So H dot, HQ can go to 0 if the fluid bounces. If the fluid expands, then bounces, and then HQ changes sign, right? Because first it's positive, and then it's negative. See, look at this, A dot is increasing, fluid expanding. Suddenly reaches maximum, A dot is 0, and fluid collapses. At the bounce, HQ is 0. And then,
Yeah.
if you don't understand this, that means you have not understood my lectures.
Yeah,
If you do not understand that the fluid can bounce, that the dust layers can bounce, the energy diagrams that I showed, everything, then really you are not learning.
Yes,
So,
I think
and
so.
be worried. Okay?
Yeah, capital D rho. Now, what is the mathematically it's okay. What is different we can see, but what is the physical difference between these two?
Well, the physical, the physical difference is that one of them is a simple fluctuation.
Yeah, that is first one, rho minus rho.
And the other one is a fluctuation that is related to the average, that is compared to the average. It's you have in statistical mechanics both types of fluctuation.
Yeah,
You have the simple fluctuation, which is a simple difference,
yeah.
and the dimensionless fluctuation, in which you divide the fluctuation by the average. It's both exist. Now, what happens is the one below is better, as we are going to see now, to get analytic formulae, right? But for numerical work, they are not very good, because there are many situations in which not so much delta rho, the delta, see, the delta rho is okay. This is okay. This is okay. Because this one below is never going to be 0. See, density in a cosmological context is not 0. It can be very low, goes to the background, can be very high, but it's not going, and it's not going to change signs, because negative density makes no sense. But negative expansion makes sense. Negative expansion is collapse. And negative curvature also makes sense. Also, this is this thing, okay, this is also tricky, because there are situations in which the curvature can be 0, can change signs. See? Is what I was mentioning. You have a region inside where curvature, spatial curvature, is positive. And therefore you have expansion, bounce, and collapse. And this is smoothly integrated into a region, an external region where the curvature is negative. So KQ, which determines this, is slowly changing, becomes 0, and then is negative. At the point where it becomes 0, this thing diverges. This delta diverges. So numerically, that's not very good, because if it's analytical, well, you can say it diverges and the paper doesn't, see. So you get something, you're writing in the paper, right? Suddenly something becomes infinite, and the paper doesn't hit you in the face, right? The paper doesn't say anything. The paper is, it's there, and nothing happens. Maybe you have to use another page to write. But if you are doing computer work and one of your variables goes to infinity, your system crashes. It starts going into circles, 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 and it can crash. So that's bad. For numerical purposes, we don't want a variable that in very, very innocent and normal conditions, the variable will diverge. So for numerical purposes, the big D is better. Safe for this one. This is okay. So we can use a combination. We can use as variables, we can use this combination. We can use this combination. This is the golden combination. We'll explain why. Because if we use these variables, these fluctuations as variables, we can establish a very nice correspondence to cosmological perturbations. Yeah, okay. So we have this, right? Local density has to be found by this way. Then local spatial curvature, very similar. We're going to find them now.
Either.
What's that? Okay. Okay, the Hubble scalar, very similar. Now, the electric Weil tensor, with that one, we already know what it is. Because we have found, in one of the Maple worksheets, we found this expression, right? This expression, what is this? This is, we already know that this is 4 pi by 3 of the quasi-local density. So this one is already, so now we can say, we can trumpet. The electric Weil tensor scalar is the negative of the density fluctuation. Right there. That's a very nice result, because this is a very important scalar. And this scalar is nothing other but the simple fluctuation of the density with respect to the quasi-local density, which is very nice, because this expression gives a covariant interpretation to the quasi-local density. We'll see that later. Now, the problem is shear. What's the shear? What's the shear tensor scale? The psi. What is the psi? We'll find out. Follow this Bollywood drama and it will emerge. So, now, let's start with the local density. Okay? Remember the formulae that we arrived yesterday, right? Remember I told you, these formulae are very easily, the only thing you have to do, you have this integral definition and you take the derivative of that, right? You take the derivative of this, you obtain this formulae. And then y gamma, because remember, this is important, we can always translate gamma is 1 plus r a prime, right? This is gamma, okay? Now, we already know that r is a r, right? Okay, so what is r prime by r? Just substitute. And do the operations. It's very simple. Just do the operations. Right. Okay. Now compare this and this. See? notice that gamma is simply, right? Multiply this times r, you get gamma. Okay? Very simple. Elementary mathematics. Okay. Understood? If somebody does not understand this, that might as well jump out of the window. No, not wasting his time or her time. Okay? So you should understand this. And also, delta rho, well, delta rho is this thing. And therefore is R. Okay, very simple. And these are the formula that we're now. Important thing. What are these quantities evaluated at an initial slice? Remember that an initial slice, gamma becomes 1 because A is 1, and therefore A prime is 0, right? So this is a fluctuation, the initial fluctuation. The initial fluctuation is essentially the radial derivative of the quasi-local density. The initial relative fluctuation is the same thing but divided by rho q0, exactly. Okay. This is a fluctuation. Now, as an exercise, how do you relate these quantities to the old variables? Remember the m, capital K, and Q. How do you relate them? Well, very simple. You relate them, because you bear in mind that m right? So, this means that okay, so this implies that okay, very simple. Now, if we multiply this times r by 3, then what we get is this is ratio. What we are comparing is the logarithmic derivative of m cubed. Well, it's this ratio. You can have a, but it's easy to do that. Very easy to reduce it. And the same thing here you can do. Simply use this formula, and you can always translate to the old variable. Now, when you see this here, when you see this, it's just some gradient, some radial derivatives of m. Doesn't say anything. Has no meaning. If you, for computation, for the purpose of computation, you can compute. But what's the meaning? What's the meaning? I asked, for example, a colleague who is very unwilling to look at these variables. He says, well, all my codes are here, I compute everything I want, I don't need these variables. So I asked him, when you see this, what do you see? What's your interpretation? says, well, it's just a quantity I have to compute. And it says nothing. It says nothing. On the other hand, this quantity, this is an initial, this quantity says something. It's telling you that it's a relative fluctuation with respect to a weighted average. Okay. This is one of the main advantages of these variables. It's not only that you are changing names to the variables, but you are finding interpretation for these variables. It's not just something you have to compute. This is very boring. This is very mediocre, in fact. I'm just computing these things. And what do they mean? I don't care. I just compute. I compute. I wake up in the morning, I open my eyes, say compute, 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 compute. I wash my teeth, compute, compute, compute. I have breakfast. Sir, what do you want for breakfast? Compute, compute, compute. Then I sit down, I arrive to my own life, for example, understanding concepts. But modern science, that's why you have to be very rebel. Modern science is becoming a computing machine. You compute, 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 and get grants, publish, 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 publish. No, people have to put an end to this, to not allow this to become so obsessive. Well, of course, we have to publish. I'm not saying everything has to be thrown away and nobody publishes, nobody computes. That's not the case. To compute, to have efficient, to publish and so on. But people also have to have time to think what they are computing, right? So here, all what we are doing, some people would say, you're wasting your time. You can use these variables. They are good. They allow you to compute. Don't waste your time. So, yeah, and then, okay, you can compute everything. You can use this type of variables. You compute everything and so on. But here, there are new variables, which are also good for computing, and have the advantage that they have a meaning. Rather than say, I'm going to take the function m and subject it to these derivatives, what you are going to say is I'm dealing with a quasi-local fluctuation, relative fluctuation. It's very different. I'm just having something that you are going to compute, right? Okay, so we use this formula. Now, once we have this formula, immediately we substitute. Because remember that we already know this. See, we need to find this. But we already know that rho q is rho q0 by a cube. So we take this logarithmic derivative. Very easy. Right? And that's the result. You should do that. I'm omitting some steps here. But this is a result. You simply substitute the thing above and use the scaling law of rho q, which is rho q equals rho q0 divided by a cube. Just put that, substitute, do some algebra, and you get to this result. Which is a very nice result. And in fact, once you identify terms, you can immediately reach this. Say, 1 plus delta is 1 plus delta 0 divided by gamma. In a sense, gamma is like a propagator. It's given initial conditions, you divide them by gamma, and you get a 1 plus delta any other time surface. And then there is also an expression for big B. So now we have an analytic expression for the quasi-local density and for the density as well, right? Now you are going to tell me, yeah, but we don't know how to compute gamma. That's true. You want to see that again. So, to compute the local density, you need the fluctuations. To compute the fluctuations, you need gamma. We still don't know how to get gamma. Well, I showed you in previous days how gamma is computed. But for computing gamma, you need to have an integral of the Friedmann equation. Otherwise, you cannot compute it analytically. For this reason, it's only possible to do it in the case lambda equals 0. Lambda equals 0, everything can be done analytically. Lambda different from 0, then you have to do numerics. Now, so you want see that? Very nice, right? People agree that it's very nice? You can say, no, it's not very nice. Not going to fail you if you say, no, not very nice. But it's nice, right? Okay. The electric Weyl tensor scalar, well, it follows directly because it's basically proportional to the density fluctuation. So immediately, we get also an expression for, you can already compute. If you know how to compute gamma, then that's it. You have an analytic expression for it. Okay? Spatial curvature. Spatial curvature, we do the same. It's more complicated, but it's the same. We apply the same formula. See, delta would be k times delta. This has to be understood because small delta is the quotient of dt divided by k cubed, right? And then this, we just simply substitute and do the algebra, and we obtain this very nice scaling law. It's 2/3, very similar to the one above, but with a 2/3 rather than a 1. But it's very similar. It's very similar. And then once we have these expressions, we can compute the local spatial curvature and get this formula. Right? So this can also be computed. And again, how do you relate these quantities with the standard variables? Well, you simply substitute. See? Now we've seen that delta 0 rho is just yes. And by the same token, you can show that well, we can do it. So, for example, delta 0k, this will be r divided by 3 k cube prime over k cube, right? Okay. This is actually like a curly k. But we know that curly k is Latin k divided by r squared, right? This is the old variable we had in the metric, right? You remember that, okay? Now, this will be equal to r by 3, and then k, and this is k prime by k minus 2r. So this will be This is delta K, right? It's very easy to find them. So you're related to these things. Now, this tells you nothing. This tells you something. This tells you nothing. This tells you something, right? So that's the advantage of using this. It's a conceptual advantage. It's not. It's also computation, but that's not so important. It is conceptual advantage. Now, how do we get this? Well, this is the initial slice. So, how would be the formula for delta rho? Delta rho, here we have it. Delta rho is this. Well, it's going to be R, and then we already know that, well, it would be M by R cubed. No, the logarithm of this to be M prime over M minus 3. It's a, well, you could say probably this is like the derivative of log M with respect to a derivative of log R cubed. But still okay. But that doesn't say anything either. It doesn't have the information that this has information, and as we see, it is also a covariant quantity related to curvature invariance and so on. But nevertheless, this is important that you know that all this we are doing you can always translate to the old variables. And for example, suppose you are reading a paper that uses the old variables. So you check the calculations, and you can also translate to the variables I'm teaching you. Then you can also translate them, right? So these are simple ways of different variables of studying the same models. And it's good to know both of them. That's why I also showed you the other ones. So you know the other ones are there, these ones are here. And obviously, in some cases, there is one case in which the old variables perhaps provide a simpler, it's a simpler description. A case when the Big Bang time is mathematically simultaneous. Because in this case, the people using the other variables simply said T bang bang equals 0. That's it. They forget about it. On the other hand, using our variables, we have to, you remember, we have to solve an implicit equation that relates rho q0 and kq0. And that implicit equation has to be solved numerically. So it's more complicated. So only in this case, when Big Bang time is set absolutely mathematically to 0, then the other type of variables are better. However, setting the Big Bang time to mathematically 0 is not a good idea, because in nature, in cosmology, something like that, nothing is going to be mathematically equal to 0. We're dealing with trillions and trillions of particles. So to say that it's mathematically 0 is an idealization. And we can say that that the Big Bang time is not simultaneous, but it's almost simultaneous. See? So that approximation, that can be worked out also. But if you want to have a mathematically constant Big Bang, then the other variables are better. But that's the only case I can think of. In any other case, these variables are superior, computationally and conceptually. Okay, so now, okay, no perturbation, nothing, because say perturbation is approximation. No approximation here, everything is exact. But it looks like the linear approximation formally, right? Except that this is exact. Right? The linear approximation just a very poor approximation. This is exact, but it looks formally the same. So that's a nice feature. So we get here, notice how you are able to compute the fluctuations associated with Hubble. Because remember that in the previous slide, we already have expressions for d rho and dk. So just substitute these expressions and that's it. Yeah? Yeah? So, the standard Hubble scalar and the shear eigenvalue. First, h, we can compute it immediately like this. We simply substitute. So this is going to be h. Want to compute h? There it is. We already know, and we did in the previous slide, I showed you how you can compute these quantities, right? This is in the previous slide. You already have analytic expressions for them. So you only have to substitute here, okay?
That means here we are just putting each and every scalar or some quantity in terms of fluctuations.
Yes.
We are trying.
The idea is that we're going to change from we're going to make a shuffle of variables that in such a way that the dynamics of the models is determined by by two Q scalars and two fluctuations. But we can shift them, we can rotate them, we can transform. There is no unique representation. There are many representations. But the representations will need two Q scalars and two fluctuations, always, right? So.
And in this manner, we are considering anisotropies and inhomogeneities.
Of course, yes. Yeah. No, we've never been, we've always been considering, because the models are inhomogeneous and anisotropic. Yeah. But we've derived some variables which mimic the variables of the homogeneous subcase, the FLRW, right? And then we're constructing other variables that describe the difference between the FLRW and LTV. These are the fluctuations. We need both. The Q scalars remind us that there is an FLRW subcase, right? The Q scalars. And the fluctuations remind us that it's not Friedman-Robertson-Walker. Yeah, you are related to him, but you are not him, right? Okay? So this is DH. If we substitute all what we did in all the analytic formula for DH and so on, this is what we get. This is a formula. Of course, everything can be computed once we know how to compute gamma. Everything here can be computed, right? Everything. These are, in fact, these are initial conditions, right? These are initial conditions and so on. So everything, this can be computed analytically as long as with the average values, and you have and then you can do a lot of, you can get a lot of information on how local quantities vary with respect to average, right? The standard deviation is one type of fluctuation. This is standard statistics. This is standard. This is not a mathematical thing that comes without any meaning. That's the opposite. These quantities have very direct physical meanings because you are comparing the local density, right, which varies from point to point, to a density that is obtained through an averaging process, right? Comparing density with local density with average density. That's the definition of a fluctuation. It's a direct comparison. So no, they do have. But it's good that you ask this question because maybe lots of other people had this question, but they did not think, well, let's ask it. No, 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 it's good that you ask the question. That's very good. But then again, I say, they're not simply mathematical. Well, now, how are you going to be convinced? Perhaps what we need to do is to do some exercises so that you can be. I'm going to show you also numerical work on these fluctuations, right? Okay, so I do have some Maple worksheets. In fact, today, perhaps after the lecture, just before going for lunch, I'm going to show you, well, the idea today is to obtain evolution equations for the models that are based on these variables. Now, once you obtain these evolution equations, you see that the evolution equations for these fluctuations, they generalize the linear perturbations. So that's another physical interpretation. These variables, these fluctuations, are exact generalizations of linear perturbations in cosmological perturbation theory. So, okay, the shear scalar. What do we do with the shear scalar? Let's compare the left-hand side with this result comes from Maple. We compute the shear, and it's computed like this. It's it. Now, we already know how to translate these derivatives into the new variables. Let's compare with the delta H. The delta H, the DH, sorry, not the delta, the DH, is this quotient of derivatives. But now we know that HQ is R dot by R. So we have to do this derivative and divide by this one. So here, I'm just writing this term here, and performing this derivative. And if you do the algebra, you can see that delta H is minus sign, minus sigma. So there we have the interpretation of sigma here, or this interpretation. We see that sigma, which is a shear scalar, is simply the negative of the fluctuation of the Hubble scalar. It's this quantity. But we can also show that it is this quantity. It is the derivative. This is a set, because here, notice that the dot and prime can be exchanged here. So this is also the derivative, the logarithmic time derivative of gamma. So there we have an interpretation for the shear scale. Okay. So now we have them all. We can compute all these quantities analytically, right? We can compute them all. Oh, glitch. Sorry. Let me correct this glitch. Alternative representations. But before doing that, let me write here a sort of dictionary. We know we have rho equals rho Q plus delta rho. Okay. We have H equals HQ plus delta H. Okay. Okay. And then we have psi 2 equals minus so notice how the original set of variables can be replaced by a new set of variables. Here the nice thing is that we had these variables before. Right, we had these variables. These are the 1 plus 3 variables, right? And they determine the models, right? They completely determine the models, right? Okay, so now we have this set of variables that they also determine the model. Except that notice also that this set of variables has a very nice interpretation because it's quasi-local density, quasi-local expansion, and their fluctuations. But we now have, it's very nice to be able to describe this scalar, the psi2, as a fluctuation of density. And the shear scalar is simply a fluctuation of the Hubble scalar. See? In fact, we know that the electric Weyl tensor can be expressed in this form. And the shear tensor can be expressed in this form. These fluctuations determine the shear scalar and the shear tensor as well. They determine. Okay. But there are several representations of Q scalars that we can construct. So far, you can say that, for example, this would be the representation of Q scalars based on, we need 2 Q scalars and 2 fluctuations. But we can change the scalars and we can choose different scalars and different fluctuations. See, for example, well, we'll see. Now, one question people might be asking, what about the special curvature? Well, we can also use these variables. We can also, instead of say, for example, we can use these variables also. Yeah, we can use these variables also. How do we pass from these ones to this? Well, we need an expression that will relate these two with those two. And what's this expression? The Friedman equation, right? Because we have this relation let's take the cosmological constant to 0 for the moment. Right? Let's take it for the moment. So see, you can always eliminate h from here. You can say, well, h, if I substitute h, and then you can always see what I'm saying is that here you have rho and h. But if you replace h by this, then you have rho and k. And you can also have formulae relating, you also have this formula. Right? You also have this formula. So you can always replace H by a combination of rho and K. Okay? And then you can use these two as your variables. The point is that the quasi-local variables and their fluctuations are always related by constraints of this type. And these are algebraic constraints. And they are very simple constraints. In fact, they are linear constraints. Right? So you can always be replacing the Q scalars. Let's show another example here. See, first, what I'm going to show is that a function of Q scalars is itself a Q scalar, right? If A and B are Q scalars, then any function of them will also be a Q scalar. Why? Because of the chain rule. Because of the chain rule, the radial derivative of Q will have this form. But then notice that this depends only on A, B, and C. This thing here, this will be a fluctuation. This is no more gossips. No, because gossip is bad. You have something to say it loud. Don't gossip, okay? Either silence or people speak up, but no gossip, okay? Now, this is a fluctuation, this is a fluctuation, this is a fluctuation, and the terms like gamma and R and so on cancel out. See? Now, the other thing is whether this integral law is satisfied. That is not necessarily the case, because if this is C, and this is C, and this integral sometimes might not say, well, forget about this for the moment. But this point here is important. Now, the exact fluctuations from here to here would be this. See? This leads to a fluctuation, and there are some algebraic products. There are gamma and R and everything. But these algebraic factors will appear here and will appear here as well. So if C is a function of F, is a function of A and B, and A and B are Q scalars, let's say the density and the curvature, and you have some function of the quasi-local density, quasi-local curvature, then the fluctuation of this new scalar is computed easily by the chain rule. It's expressed in terms of the fluctuation of A and the fluctuation of B. It's a sort of linear combination, right? So now, once we have if this is CQ, then people might ask, well, what is C? What would be the quantity that we are averaging? And this quantity is obtained by the standard rules. So now this quantity, this primitive scalar, may not have a simple interpretation, because we know that the primitive scalar of the quasi-local density is the local density. The primitive scalar of the quasi-local Hubble is the local Hubble, and the same with special curvature. But we might define functions of them in which the primitive scalar has no simple interpretation. Okay. So, but anyway, this is the, is this very well understood? Because we're simply using the formulae. We're simply using the formulae. Like, we know that CQ prime is this thing, or let's say it's this. Right? But But the same thing, it happens the same is with the other ones. The other ones will also have this factor here. For example, AQ prime will also have this factor. Right? So if we know that CQ is a function of AQ, BQ, then its time special derivative will be this will be, using the chain rule, plus the same. So you see how these factors cancel out. This 3 gamma, this thing here, they cancel out. So you get the relation just between the fluctuations, right? Okay? Okay, let's see an example of this. Very illustrative example, because while you can have all sorts of representations, basically there are two important representations. The one in terms of the density and Hubble, and one that we can construct in terms of omega parameters. These are the two most interesting configurations. The omega factors, see? We can define these omega factors between Q scalars, right? They mimic the FLRW omega factors. They mimic them. But be careful, because it's constructed between Q scalars, right? And notice that these are, for example, you can say omega matter, it's a function of rho Q and HQ. Therefore, it is also a Q scalar, right? Because it is a function of two Q scalars, it is itself a Q scalar. And then the same with the omega lambda. It is a function of lambda, right? It's also, which is a constant, right? It's also a function of HQ. And the curvature thing also is the same thing, right? Okay? Now, in the case of omega Q, I know that omega without the Q is just the local density. But in the case of omega, what is omega without the Q? It's not, it's difficult to understand what it is, but we don't need it. See, we don't need it because in the system we're going to construct, the variables will be the Q scalars and their fluctuations. We can construct fluctuations of these objects. And we can do a dynamical system, or we can study the dynamics of the models in terms of this. Now, what's the use of considering these variables? Because they mimic cosmological variables used in cosmology. They are very well understood. And numerically, it is always better to work with an omega factor, because omega factors are bounded, are quantities of order 1, while density, well, density can also be normalized, but yeah, it's also possible, but density without normalizing can be would be forcing you to work with very small numbers or very large numbers, right? Anyway, let's see the formula. See, we can use the Q scalars, right? These Q scalars instead of the other ones. Instead of rho, K, here, K, HQ, etc. There is a Q missing in the K, right? It's a typo.
Yeah.
Okay. Now, H itself can be expressed And here I'm setting the cosmological constant to non-zero. H itself, HQ, can be written like this. It is just writing the Friedman equation in terms of the omega factors, right? Okay, it can be written like this. And of course, this can be related to the all variables as well. Again, I'm writing this so you can see that the connection with the all variables is not lost. However, if you see the thing to the right and the one to the left, here, this thing says nothing. This is something, it says nothing, but this thing, it has more information. Now, remember, these are not FLRW quantities, but in the limit of homogeneity, they do reduce to the FLRW quantities. Okay? So, this is omega here. How do we pass from here to here? Simply substituting the scaling laws for H and scaling laws for rho, you get this. And this is identical to the FLRW scaling law of this parameter. Now, again, I write this in terms of the all variables, it would be this. But here, this tells you nothing. Nothing. But here, this is important because it mimics an FLRW scaling law. Now this is the curvature, this one here, the scaling law takes this form. And again, in the all variables, it would take this form. And this is the lambda. Now, it's very interesting to see what happens when A is almost zero. When A is almost zero, this thing approaches 1, right? And this thing approaches 0. Okay? If A is 0, this goes to 0. And this also goes to 0. So for very close to the Big Bang, which dominates? Omega matter. And it is close to 1. Yeah?
Yeah, you said total omega should be 1, total omega k, omega m, and omega lambda. It should be 1.
Near the Big Bang.
Near the Big Bang.
Near the Big Bang.
Not at present.
Eh?
Not at present. Not at today.
No. Near the Big Bang.
Near the
Omega matter today is not close to 1. Total
Yeah,
omega.
total omega should be 1.
Total omega, yes, but no, but this is just omega of matter.
Yeah. So, are there some observation constant on individuals omega? Omega k?
Yes, there are. Of course there are. You have the omega of cold dark matter, the omega of the baryons, the omega of the photons, of the neutrinos, of curvature. Yeah, you.
Yeah, for example, in FLRW universe, we have omega n, omega m. I mean to say, there are observational constant from W map and Planck map.
Yes.
So same thing is happening for this model also.
No. Because this model is very different from an FLRW model.
Yeah.
No, these quantities, they are not FLRW quantities. They
Yeah.
resemble them.
So we
They
cannot
resemble them.
we cannot find the value of these quantities using
No.
operations.
You're talking about completely different thing. You're talking about observations that are fitted by satellites, assuming an FLRW model with perturbations, right? So these observations are fit with that model, with respect to that model, which has nothing to do with these models.
But if we take the base this model to as a base, there we are taking FLRW as a base to fit the observation.
Yes.
If we try to take this as the base for the observations, then what we will?
No, well, you have to compute the, no. This, if you calculate observables here, it depends on your assumptions. There is no general answer to this, because it depends on what are your assumptions for this part. Depends on what do you assume for your density, for your distribution, and so on. There is no general question. There's no general answer to this. These are models that can describe a large variety of profiles, of density and curvature and Hubble profiles that are inhomogeneous and are not perturbations. So wait until we get to observations, and it will be clarified. But look, no. This is what I don't want, did not want, but it's happening. These are not Friedmann-Robertson-Walker parameters. They are written, they mimic them, but they are not Friedmann-Robertson-Walker parameters. They are not, write that 1 million times. They are not FLRW parameters. Observations of W map and so on are fitted with FLRW parameters, right? But these are other models. This is a generalization of FLRW models, right? Now, whether this generalization can explain or not observations, probably not. Unless you go to the perturbative, see, these models reproduce FLRW models in the homogeneity limit. That is, if you have inhomogeneities and you start smoothing them down, ironing them down, and it slowly becomes homogeneous, then you recover in the limit, you recover FLRW model. Okay? Now, suppose that you don't go all the way to the limit, but you tolerate a small bit of inhomogeneity, then probably these models could satisfy the observational constraints of WMAP. WMAP only gives you data. WMAP itself, or Planck, they don't tell you, yeah, the model is this, and this is what you obtain after analyzing the data. The satellites only give you data, redshifts and luminosities and so on. They just give you raw data. Now you take that raw data and you try to fit it with a model. See? The best fitting model so far for all this data is a model in which the geometry is FLRW, the spatial curvature is 0, and the cosmological, the omega lambda and the omega, they have specific values, right? That's the best fitting, right? Now, how could these models be incorporated in such a process? You could try to find the LTV model that best fits this data. And you could probably find one, right? Probably there is one. But probably it's one that is very close to homogeneity, the one that would fit that, right? Probably, yeah. It would have to be done. But do you understand the difference? It's the satellites only give you data that you have to fit with the model. Now, we can put these models and try to fit them, but it's not, but I don't think it has been done. It has been done for some data. These models have been used to fit, for example, supernovae data, and they work very well. But you have to be careful, because these are not FLRW quantities. These are quantities that are LTV quantities. LTV quantities, they are inhomogeneous. Even though they have the same label, the same name, look, this Q. This Q tells you that it is not an FLRW model, right? Okay, now, what happens, what I'm saying is that when A goes to 0, these models approach the Big Bang, right? And at the Big Bang, this parameter, which mimics, not identical, it is a mimic of the FLRW parameter, becomes 1. When A goes to 0, this thing here becomes 1. A goes to 0, this becomes 1. Not present day, Big Bang time. the Big Bang time, not today, not today, okay? Today, present cosmic time, if we associate t equal t0 to present cosmic day, then A would be 1, not 0. 0 is Big Bang time, okay? Big Bang time, this parameter goes to 1. This one goes to 0, and this one goes to 0. What this means, that near the Big Bang, the models, all the models, irrespective of what initial conditions you choose, near the Big Bang, all the models behave with this omega going to 1, near the Big Bang, right? These models, not FLRW, these models, okay? And that has to do with observations today or anything like that. We're talking Big Bang time, not today, okay? Now, this is very nice because we have a quantity that near the Big Bang is a singularity. Density diverges, Hubble factor diverges, Hubble scalar diverges, curvature diverges. Bad, very bad. How can you work with somebody who will say hello, good morning, and it's infinite? See, not good. However, what happens with these parameters at the Big Bang? 1, 0, 0. Very nice, isn't it? You realize the question, we're working with parameters that are going to be very well behaved near the Big Bang. So they are ideal for numerical work, aren't they? Imagine if we go to a Big Bang and things become infinite, right? So it's very nice to have some variables that we go to a Big Bang and remains finite and takes very simple values, okay? So this is one of the main utilities for this, for using these objects as variables, right? This is a very good. I'm not here. So what we have to do is to transform the 1 plus 3 equations in terms of these quantities, which we will do after the tea break. Okay. Now, all Q scalars are strictly LTB quantities. They are not FLRW quantities, right? And again, it's something interesting. What would happen? What happens if A equals 1 here? If A equals 1, then what you have is that omega Q is omega Q0. So these definitions really don't make sense when omega, when T is T0, because these are like initial conditions. If we solve the model, this would be our initial conditions. So this also I'm going to show you. This quantity is a function of T and R, right? And this quantity here, it's its initial condition. This omega m q0 is initial condition for omega qm. So if this is our initial condition and it is given at present cosmic time, we can find that in such a way that it has a relationship with data when we fix initial conditions. For example, we can say that we want to fix this function in such a way that asymptotically coincides with the FLRW model, or with values reported by W map or by Planck, right? But it is in this way when specifying initial conditions when we would take the observations, right? We correspond with them. But this has to be done so you understand it. Okay, so these are strictly speaking LTB quantities. Okay, they are not FLRW quantities. They mimic them, but they are not. Okay. Now fluctuations and scaling laws. For example, let's take the omega Q scalar. this one. This one, we take it as a function. This is a function of rho q and HQ. So how do we compute its fluctuation? We apply the chain rule, and this is going to be the fluctuation of the omega. And now the primitive scalar is this quantity, but this quantity may not have, this quantity is not going to be the omega factor of FLRW. This quantity I still don't know how to interpret. But doesn't matter, we will not need this quantity. We only need this and this. That's all we need. We don't need this one and this one. We don't need it. Okay? So this is the whole idea. To take the scalars that I showed you before, the Q scalars, are given in terms of omega factors, and to transform and to find the fluctuations, and to write the 1 plus 3 equations in terms of these quantities. And yeah.
That means with the help of Q scalar we can remove singularity.
No, you don't remove the singularity. You just have variables that are well behaved in the singularity. You don't, remove the singularity. You don't remove the singularity. No, that singularity is inherent. It's something, see, the fact that you have variables that that are finite near the singularity doesn't mean there is no singularity. So how do you know there is a singularity? Because curvature invariants diverge.
And what about Q, means for curvature KQ?
What?
Curvature.
The special curvature.
Yeah.
It also diverges.
No, but if we take that Q scalar.
The Q scalar it becomes 0 near the Big Bang.
0.
Yeah, you saw it in the transparency before. Okay, now let's see how we compute the metric functions. Now, we've seen before. The metric function A is computed by this integral. So this integral, if lambda is 0, then we've seen how it leads to very simple solutions. Otherwise, it has to be done numerically. If we use the omegas, then this quadrature simplifies, because the h comes out of the integral, and then QA has this very simple form. So this is also preferable. But anyway, we have to do this integral. Whether one way or another, we have to do it. Okay? So, and that's the trick. If lambda is greater than 0, then very likely it has to be done numerically. Now, here, the Big Bang time can be obtained as a function of the other functions by, if we take this integral here, right? We take, or this one here, doesn't matter, either one. And we set time equals to t to t0, then A has to be 1. Because remember that A evaluated at t0 is 1. This is a coordinate choice we made, right? So once we substitute that, we notice that the Big Bang time can be expressible as a function. What function? Well, is this quadrature. It's a function. It has to be, or can be written as an integral, also evaluated from 0 to 1. So then all this is a function of these variables. Now note, in the case omega greater than 0, the integral f is expressible in terms of elementary functions. Okay? So in that case, then f has an analytic form. And then you can use it to compute the function. The metric function gamma is obtained when lambda equals 0. When the gamma function is obtained by differentiating both sides here. You differentiate both sides with respect to r, and then you obtain a prime as a function. But it's if you do not have an analytic expression for f, then it's not possible.
No, then it's not.
It's not possible. But if in the case lambda equals 0, then we can obtain an analytic expression for gamma. Now, I don't know if you remember that we already had derived this quantity before,
Yeah.
right? Now, we know that mu and k are simply the initial density, quasi-local density, quasi-local curvature. Now, this quotient, we already can relate it to this, right? We can relate it to this quantities, right? This quotient. And so this is the analytic expression for, now notice that this is f. This t minus tvb is a function f that we get here. So once we get this form, so this is the analytic expression. You can compute this analytic expression if you have this formula, right? Now, for lambda different from 0, this is not true. Different, right? It's a completely different thing, okay? But if lambda is 0, then that's a formula. So you simply substitute this into the formulae. See, if you get this integral,